So what I'm going to talk about is about GPUs. The hot topic, the underlying thing that powers everything else. So I'm going to talk about that. So specifically I'm going to talk about how we are going to open source a stack and what proprietary lock-in we are in, right? We hackers have this anti-authoritarian sort of ethic, right? I'm deeply into that. Like I'm very anti-authoritarian in terms of like I don't want to be dependent on anyone. I'm right now dependent on someone. I'm going to talk about that. So I'm going to talk about three things. So specifically, what's the proprietary dominance we are in? Like who is dominating us? Who is the guy? Who is the big brother controlling all of us, right? And talk a bit about the computers themselves, what the computers look like from inside. Like we don't give a damn. Like for us, this is a computer. Like I don't know how many of you folks realize this is a computer. So I want to have a sneak peek inside a computer, see for yourself how it works, right? And finally, we're going to break the wall. I mean, we're going to figure out how we are going to break the wall of this proprietary dominance by someone, right? So here's the big brother controlling us. And who's that? Who's our big brother? This is a stock price. Can you guess? Who's this? Whose stock price is this? This is in August. Yeah, it's NVIDIA. So, and it's 8:15 now. Exactly. It's like this is 6 months old stuff. The price was 37 in 2019, and now it's like crazy, man, crazy. So, I mean, let's take a step back and talk about history of AI itself. How AI started. So there were many boom and bust cycles for AI. I'm really worried that this might be another boom that will eventually burst. I'm really worried about that, but so one such burst was in 1970s, another such burst was in 1980s. So these are called as AI winters for people who have never heard of it, right? And there was an inactivity of AI. People thought like AI is useless, and there are scammers who are like scamming all of us in terms of AI will do this, AI will do that. So this particular time, there was a revolution that started in 2012. It started because of three things. One, open source research and open source code. Like, well, this hackathon is proving that. See the kind of stuff, we are able to do it in 2 weeks, 2 months. Second, huge amount of data. So we got access to, so the whole revolution got started when this Stanford lab has open source ImageNet, the data set on which everyone benchmarked and tried to beat, right? And finally the compute, the GPUs, what we are going to talk about. Right? These are the three ingredients to what made the current AI revolution happen. And it all started in 2012 with AlexNet. So these are the three guys. This is a gentleman who set me on this path, Geoff Hinton. He said that radiologists will be like outdated, you don't need them. And then this is Ilya Sutskever. I don't know if you have heard him. He's the OpenAI guy behind all the drama that happened recently. And that's Alex Kristowski. He's the guy who actually, PhD student who actually wrote all the code, right? So this is cited by like 100,000 people, like crazy. And they use GPU from the get-go, right? As I spoke about. So why GPU? What's so special about GPU, right? AI runs on GPUs because AI uses a lot of linear algebra operations, specifically matrix multiplication, right? And these are highly parallelizable and GPUs are really good at it. So for comparison, CPU would have like less than 32 cores, like your system probably has like 8 cores, 16 cores tops. But GPU has like 4,000 cores, crazy. And CPU, because of this, is 10 times slower than a GPU, right? And it's impossible to train and sometimes even infer AI on GPUs, right? And CUDA is a de facto standard. For me to program a GPU right now, for me, CUDA is pretty much the only way for me to program the GPU, and it is C-like language that works on top of NVIDIA GPUs, and you can basically program GPU to do your matrix multiplications and whatnot. Well, this works only on NVIDIA, and that's exactly why we are all like our big brother. We are all dependent on NVIDIA because like our AI cannot run or get trained on anything else, and we have to go ask a lot of people, give me credits, right? So all that stuff because we are in a monopoly, right? And this is not cool. I mean, monopolies, they get stagnant. See Intel. I mean, I'm a fan of Intel now. See what Intel was like. Intel, they missed so many buses and they held back Moore's law for like 15 years now. Not cool for the community. We should not let monopoly happen, right? AlexNet, of course, was done in CUDA in 2012. So this is the reason why we are stuck with NVIDIA. So and of course, PyTorch, which dominates AI framework, is also written in C and CUDA, which means that PyTorch works natively only on NVIDIA GPUs, right? I was one of the co-authors of PyTorch, by the way, so I know this intimately. So this is the reason why, you know, there's so much fighting going on NVIDIA GPUs. Now, like there's a measuring contest of I don't know what of people between like, hey, I have this many GPUs, I have that many GPUs. Like everyone is like, Meta has like 1,000 GPUs, I mean 20,000 GPUs, and like India is saying I am importing so many GPUs, and like big news. All that stuff precisely because like the demand, NVIDIA's dependence we have on them, and nobody else can like satisfy the demand. And for reference, I don't know if you know this, a GPU costs $30,000, H100 GPU. How many of you make 30,000 per year here? Like, can you raise your hand? How many of you folks make 30,000 per year now? Crazy, right? Like this stuff costs more than your time, man. Like this stuff costs more than your time per hour. Like if you want to rent something from cloud, it costs more than what you earn per hour. Like this is like machines winning over us. Cannot let us happen. So let's talk about computer architecture. Let's try to peel inside the computer and, you know, see what's inside, what's happening inside. You know, we all see all these nice boxes. What's happening inside, right? So here I spoke about this guy who built atom bombs using computers. That's exactly why he was wanted. He wanted to win World War II, and one way to win World War II was Project Manhattan, and they eventually dropped it on Japan. So this guy wanted to figure out how to place the bombs around atom bomb so that the detonation happens very nicely, right? He's like fluid mechanics guy, mathematician. So he used computers to do that. This is his computer. He built his computer. He built his own computer, right? And when he built his computer, he had created this architecture called as von Neumann, now called as von Neumann architecture. Believe it or not, this was also inspired by Brain. Everything was inspired by Brain in computers. They used to call, if you read his original paper, it's he uses words organs, he uses words neurons for connections, all that stuff. So the underlying principle of his architecture is you have two things. It's important. So please pay attention to this. Like if you don't pay attention to this, you might miss a lot of talk. So there are two parts, a controller and a memory. So there are two organs, and then there's wires connecting them, sort of like a circulatory system, right? So you have two things, a controller and a memory. You can think of it as like two brains, right? You have left brain and right brain. Or you can think of it as like your system 1 and system 2 in psychology. So these are the two systems that we have, a controller and a memory. What memory stores both the program and the data. Controller basically interprets the data and executes the program, right? So that's what basically this architecture is all about, controller and memory. So it's important to know that there are two organs here that needs to be in balance, an in and ang, right? And this, by the way, is basis of all the computers. Even now, this has been done in like 70, 80 years back, right? You might think like, hey, this is outdated and people have moved over to it. Nope, this is like so fundamental. So this is a motherboard, by the way, it's made in India. For unbelievers, for people who don't believe manufacturing will come, like this is made in India. So this is a slot for CPU, this is a slot for memory, and then the wires connecting them. Literally von Neumann architecture. And you might think like, hey, GPU will be different. Like is GPU using non-von Neumann architecture? They have done something cool? Nope, it's the same. So you have the chip, you have the actual controller, and then you have memories around them. So this, by the way, like when you see a card, you have the fan in front of it, you remove the fan, this is what you see, the bare PCB, right? So even this is von Neumann architecture, right? And this, by the way, is somewhat complicated. I will, if you don't follow it, it's all right. So this is GPU architecture. Uh, so to simplify what GPU architecture is, it's basically your multi-core processor. It will have like 16 cores or whatever. Each core can support hardware threads. See, we usually are used to software threads, but a GPU supports hardware threads, threads that are supported by the scheduled by the GPU itself. So it's vector processor with multiple cores. That's what GPU is. There's something called as memory hierarchy. So where you have, so this is actually very interesting. I'll just give a thing because see, memory and controller has to be similar speed, right? We cannot actually do that easily. So what we do is we put memory close to the processing. Some memory, not too much. For example, here I have put something called as register file, which is very close to one of these cores, right? And then I have also created something called as L2 cache that is close to each of these cores, right? Which is shared between all these cores. And finally, I have the final main memory, which is this. So hierarchy 1, like lowest part of the hierarchy, slowest memory. So fastest memory, which is shared across all the cores, and one memory, which is exactly in each core. So this is the basis of, now you can say, hey, you understand computer architecture. No, I have 20 minutes. So optimal hardware design. So this is the LLM design that for example, right now the topic of interest is LLM. So I have done some math. I'll not explain through it. I have done some math and I have basically found the optimal flops to bandwidth ratio, right? Which is basically like from maths, you have two components here, controller, memory. So when you run your inference, like if one of them is slower, your system will be slower, right? So you want both of them to be equally fast, right? Which makes sense because like when you have two organs and one organ is not functioning, the whole system will not function, right? Whole body will not function. So you want them to be equally functional. So that is measured by the fact that controller speed is measured by what is called as flops. You will keep on hearing that in a lot of places. And memory speed is measured with something called as bandwidth. I'll not explain you the terms, what they really mean, but you have to know that speed 1 and speed 2. And the ratio of the speed determines the balance of the machine, right? How well your machine is architected. So if you are doing LLM training or inference, the optimal ratio between them turns out to be batch size, right? So in case of, what's batch size for inference? Like usually what's the batch size for inference? 60? Like when you infer, you usually only have one batch to process, right? So, or maybe 3 batches, like number of concurrent requests. So you usually have batch size of 1, which means that the optimal ratio for inference is actually 1. Both of them have to be similar speed. But here's the crazy part. The flops, this balance is getting worse and worse towards controller. So controller is becoming faster and faster, memory is becoming slower and slower. I mean, relatively, right? So the ratio of speed of controller divided by memory, right? I'm showing this here over the years. As you can see, over the years, the balance is getting 20% worse every year, right? And currently the balance is 100. So which means that my controller is 100 times faster than my memory, which means that the best way I can use my current chip is training, and only training, because batch size of 100, who does batch size of 100 inference, right? So this is the problem. So we need newer designs for inference, and thankfully for us, there's a Cambrian explosion. There's a Cambrian explosion of AI chips that we have. I'll just walk you through the names of these people. We all recognize him hopefully now. That's Jensen, NVIDIA's chip, latest really big chip, as you can see. This Pat Gelsinger, this Intel CEO, holding really, that's AMD, Lisa Su, right? And this is Google, Sundar Pichai. So his is TPU, and then this is startups, many startups. Like I showed you my favorite startup, which is Jim Keller. He designed your machine, by the way, most likely. So that's his GPUs. Many GPUs that are available for us right now. But as you can see, we are dependent on CUDA. We cannot switch to them. Like even if you want to, we cannot switch to them, right? So the market is, is stuck to training, and we cannot actually give away the power of AI to the masses. So the machine is controlling us. Like, I don't want that. Right? So how do we break the wall? How do we break this? Right? So this has been a problem even for CPUs long time back. There were many different guys who were trying to build CPUs, Intel, Sun, ARM, n number of people who were building CPUs, and there was a lock-in. Intel was the guy who was dominant before, the big daddy. He was the guy. So the way people broke this dominance by using something called as intermediate representation, right? So what people do is, if you have n programming languages, people write their code in n programming languages and m different architectures. So you need to write n into m library compilers, like translators from programming language to the architecture to make it work. But the insight was, if I have to compile everything to one, say Switzerland, right? One Switzerland of all languages, and that will take care of compiling to the hardware, right? My complexity is going down to linear, n plus m. I only have to do n plus m compilers, which makes my life a lot easier, and newer architectures can come into the market, right? And so the kernels have also been really hard. Like, this is one of the other point of lock-in. So if you write, for example, what I mean by kernel, this, if you recognize, is matrix multiplication. C of I j of j equals sigma k, A of I k, C of kj. So how many loops do we have in this representation? I, j, k. There are 3 loops. So if you use 3 loops and write 3 for loops, which is the most basic implementation of you will get something like 1 gigaflop of performance, right? So this is the hand optimized code that I wrote. This has 7 loops, 6 or 7 for loops, right? So this hits 90% of the peak performance, right? So this is one of the reasons why vendors provide these hand-tuned libraries, and we are stuck using to them, right? So, but thankfully, there is an alternative to CUDA now. A portable alternative to CUDA is possible now, and it's called as SYCL. So SYCL is a standard, just like how UPI is a standard. It's not controlled by single bank, right? SYCL is a standard. It's a DPII in the current speak, right? It's standard, not implementation. There are three implementations that talk to each other. One from Intel, one from Codeplay, other from Adaptive CPP. It's a HackEye project, right? So there are 3 implementations which is portable alternative of CUDA that can work with each other. And this thing works great. Like, I have actually benchmarked matrix multiplication, which was hard, to vendor libraries, and I found the performance to be pretty good. Like, it's 50 to 150%. Like, that's the range. Like, it performs approximately as much as what vendor would provide us, right? And also, one of the things I found out was LLVM IR doesn't work. Like, the whole architecture that worked for CPU doesn't work, unfortunately, for GPU. Not because such a thing is not possible, but because LLVM is stunted. So like, so this is a general flow of a compiler pass for GPUs, is that you have a code, it compiles into 2 things. One, to run on the GPU itself, and the second thing to coordinate. This is run on the CPU, right? So in case of the code, LLVM code, the IR that is generated has to be device specific because of something called as intrinsics. And then the host code has to also be specific to the GPU because of drivers, because the drivers themselves are not abstracted out in Linux kernel. NVIDIA's driver, by the way, is also not open source. So how do we get out of this? Like, so one of the things that I believe in is this GPL license. You know, the way I came out of this is in a conversation in this compiler discussion group. So LLVM has a solution called as MLIR. So MLIR is trying to do the similar stuff, like trying to break the monopoly. But turns out majority of the stuff that is written in MLIR is also closed source. Like, it's like, what kind of thing is this, right? So the reason is that it's not GPL, it's not GNU public license. The code is not free. Software is not free, like free as in freedom, not free as in beer, right? The code is not free. So the reason, like, I as a community, if I wrote some code and someone else takes that code and makes it work better on their system or some other system and making money, because I contributed to it, I should get the code back to me, right? This was the basic principle of that made Linux successful, right? Because Linux was the guy who did the same stuff for computers, like operating systems. There was Windows, there was Mac, and Linux was like, hey, I will create an operating system on my own which is completely open source, but if you fork it and make it work for your system, you have to give it back to me, for sure, right? And that made Linux work. And this will ensure that I will never become closed AI, like from OpenAI has morphed into closed AI. So I will never become that either. So this is the license I'm gonna adopt. So, and you might ask, how do I make money? So here's a quote by Alan Kay, who says that people who are really serious about software should make their own hardware. You know what? I'm building hardware. So I'm building hardware. This is what I'm building, and that's my pet who has approved it and told that it's good. This is what my company is called after the scientist, and the logo symbolizes basically two halves of the brain or chip or whatever the computation you want, and I'm basically plugging them in. So that's it, I guess. I'm 20 minutes. I have done it. Thanks, guys. Any questions?
So how is it different from other open source libraries such as Nuvo, ROCm, etc.?
I have no clue what OCM is.
So AMD uses
ROCm, you mean?
Yeah, ROCm.
Oh, so ROCm is not truly open source. See, in open source implementation works for every different thing. A lot of different hardwares, people should be able to contribute to it. ROCm right now works only on AMD. Like if you go to ROCm and say that, hey, add support for Intel, they'll be like, no, this is not my priority, I'm not going to do that. So it's not really open source. It's not GPL, man.
Just to clarify, like, are you building an open source, like, intermediary language and hardware, or just the hardware, or what's the plan?
So I'm building both. So what I'm building is the open source IR, that's my software. Okay. And the software works best on my hardware, but people are free to use it to make it work on their hardware.
Will you integrate with MLIR as well, or what's the plan?
No, I think I'm strategically deciding not to integrate with MLIR and write my own library in GPL. So because of nobody able to steal it from the community.
Just one clarification. Why did you decide to go with GPL v3? Because certain companies have a inhibition to that level.
I'm doing LGPL v2. It's all right.
GPL v2. Okay.
LGPL v2.
LGPL v2.
Yeah, you can link to it, man. Okay. That's like way too restrictive. I put GPL v3 because that's the best logo I could find about GPL. But I'm a believer of LGPL v2. Got it. Good. Someone who understands intricacies of license.